Guys, it's Miss Landry, and we are on the second video for proteins. We're going to learn about enzymes today because that is most of what our labs will be looking at. So let's jump right in, starting with learning objectives. In the last video, you learned about the structure of proteins and some of their functions. Today, we're going to be looking at just enzymes in this video. So we're going to look at how does an enzyme actually work. We're going to look at the factors that affect enzymes, and we're going to look at optimal environments. So every enzyme kind of has an environment that it works best in. Well, also, it's not on here, but we'll also look at inhibitors, like how do we control enzyme activity. So let's go. All right, first of all, the shape of the protein is key. If the enzyme, the protein, is not shaped properly, and if you remember from the last video, we talked about that three-dimensional shape, it's not going to function. So enzymes work as catalysts, and a lot of times people will say, oh, a catalyst speeds up a reaction, and that's a little bit of a misnomer or a misconception. What it actually does is it reduces the amount of energy that is required for the reaction to occur. So any reaction, chemical reaction, and that's what metabolism is. Okay, so metabolism is basically the sum of all of the chemical reactions occurring in your body, and it takes a certain amount of energy. So if we look at this chart, if you notice, like from here we have our reactants, it requires this much energy right here without an enzyme for the reaction to occur. Once the reaction occurs, it becomes a product. Okay, and what an enzyme does is it lowers how much energy is required for that change from reactants to products. So if you look here, let me erase what I had there because I just made it kind of messy. So this first arrow that went all the way from here to here, that is without an enzyme. That's how much energy is required. An enzyme lowers that. So we're lowering the activation energy required. Activation energy is written as a capital E with a subscript A. So that's what activation energy is. Be sure you know how to define that. So how does it do that? Well, it does it with shape. Okay, so the shape of the enzyme. So here is the enzyme right here. Okay, so this green blob is the enzyme. And notice it has a very specific shape built into it. And that is created in that three-dimensional folding, right? So I folded this thing up and now I have this weird shape. And the only thing that's going to fit into that shape is something called a substrate. So the substrate is what the enzyme works on. Now, if I'm putting something together, I'm going to have more than one substrate because I'm going to take those two substrates, put them in there, and put them together. If I'm breaking something apart, I'll have one substrate, it'll fit in there, it'll break apart and move off. So this area right here where the substrate fits into the enzyme, oh, you can't really see that yellow, where the enzyme fits in is called the active site. So the substrate, which is what the enzyme is working on, fits right into that site, that active site, and that allows the enzyme to do its job, okay? Now there is a little bit more to in that. It's been called the lock and key model because it fits in there like a lock and a key, and it's very specific. So enzymes only work on one substrate. But what can happen is something called an induced fit model. So what happens in an induced fit model is the substrate enters into the active site. When it enters in, it causes almost like a chemical interaction, which basically induces or creates an even tighter fit. So if I'm going to show you an example of this in class as well, but picture this. Okay, so I say to someone, "Aw, come here," and I put my arms out, right? So right here is my active site. And then the person comes in for a hug, and what do I do with my arms? I don't just leave them there, right? That person coming in is the substrate. They come into the active site, and I hug, and that hug is the induced fit. So that's what happens with the induced fit model. All right, so optimal environments for enzymes. There are a few. So we look at things that can affect enzymes, and we know that they can because we can actually calculate the rate of enzyme activity. So I only want you to know 4. There's a few more than this, but the temperature is one. Okay, so let's say that I have I talked about amylase as an enzyme in the last video. And so that's in your saliva and it works to break down amylose, which is a starch. And it might have a really good, your mouth temperature is probably right at body temperature, which is 37 degrees Celsius. Remember, we use Celsius in science. So it's optimal. This is like enzyme activity right here, right? So the activity is highest at its optimal temperature, which would be the body temperature. It still works if it's colder or hotter, but eventually you're going to get to a point where it no longer works. Now, in temperature, when it gets too high, what's going to happen is something called denaturing. It's hard for me to write. Sorry, guys. Denaturing. And what occurs is some of those chemical interactions start to break and fall apart. And so the shape of the protein actually starts to break down. If you've ever seen an egg cook, like when you're making scrambled eggs, that like yellowy liquid turns into that fluffy, wonderful scrambled egg. That is the protein, the albumin in the egg, denaturing, and it's causing a change in its shape. pH can also really affect enzymes if you look here. So pepsin is a type of enzyme that's found in your stomach. Now your stomach has a lot of acid, right? So it's going to have an acidic pH. So it has a pH of about 2, which makes sense for the pepsin to work the best in that environment. Whereas trypsin, which is found in your intestines, which thank goodness are not acidic, that works best at a pH of about 8, so a little bit alkaline. So pH also definitely affects it and can also denature enzymes. The other two have to do with how much substrate you have and how much enzyme you have. So I'm going to kind of compare this. Think about making, you have like a party coming up and you want to make subs for everybody. So you have all the meat and you have all the bread and you start like an assembly line and you're just making all of the sandwiches. You, the one making the sandwiches, are the enzyme, right? So you are the one making it happen. The food is, and the bread and the meat, those are all the substrates, okay? If I have enough substrate, but not enough enzymes, I am going to lower the efficiency of work. So if I only have one of me and I need to make 200 sandwiches, it's going to take me a while, right? Like I won't run out of stuff, but I only have so many hands that can do the work. Whereas, let's flip it. If I don't have enough substrate, that's also going to affect how efficiently I work. So if I run out of bread, I can't make any more sandwiches. Okay, so that is something we're going to look at in a lab. So hopefully that makes sense. I think it does. We'll see. Last thing I want to talk about is how do we control enzyme activity? I'm only going to talk about inhibiting the enzyme activity. I'm not going to talk about increasing the, I can, if you want to learn about it, I think that might be an aspire to do. But basically we have two types of inhibitors. We have competitive inhibitors and non-competitive inhibitors. And it all has to do with whether or not the inhibitor binds to the active site. If it binds directly into the active site, it is competing with the substrate. So it's basically blocking that enzyme from being able to have the substrate come in. If it binds anywhere else, and this is called an allosteric site, you don't need to know that, but here's an inhibitor binding kind of on the bottom of this enzyme, not in the active site. But what it will do is when that inhibitor binds, it's going to change the shape of the enzyme, which now the substrate will no longer fit in. So that's some ways that inhibitors work. We also use that in medicine, but it's kind of cool. I think enzymes are just awesome. So I think that's it for this video. You guys have a fantastic time, and I will see you soon.